Today's guest today is our PhD student, Neelabh Kshetry. Did I pronounce okay?
Yeah, that's right.
Neelabh is coming from Nepal, and he finished a bachelor degree in computer science from Troy University in Alabama, and then that was in summer 21, and then in the fall he came to University of Louisville, continuing with PhD program. He's working as teaching assistant for different classes, including automata theory, survey of computer science, and data mining. Neelabh finished PhD candidacy exam, summer 2024, and his research focuses on primarily on machine learning, more specifically on explainable AI, and even more specifically is so-called counterfactual explanation. Recently, in June 24, Neelabh published a paper in peer-reviewed International Journal of Computers Communication and talking about this XAI framework, and that is our topic for today. The title of his presentation is "What if Explainable AI Framework from Counterfactuals Toward Causal Understanding." Neelabh, welcome, and the board is yours.
Thank you. Hello, everyone. Like Dr. Kantarjit said, I'm Neelabh Kshetry. I'm a PhD student. Today I'm going to present on what if XAI framework. It's something I've been working on, moving from counterfactuals towards causal understanding. Let's get started from the top. We all know AI is everywhere. We see it being implemented in places where the decisions that it makes are impacting our lives. For example, it's being used in healthcare. One specific example is it's being used to predict inpatient health trajectories. What it means is AI is being used to see how long the patients are going to be in the hospital, how serious their medical conditions are. Another use case is in finance, where AI is being used to assess loan eligibility. It's also used to detect fraud. Similarly, in law enforcement, AI is being used to detect crime patterns to prevent them. We see AI is being used in critical sections where the decisions that the AI makes are impacting all of our lives. So what is the problem? The problem is that the AI by itself is very complex and obscure. People who are using it, they do not understand it. People that are being impacted by the decisions do not understand it. So how can we trust a system that we, when we use it, do not understand? That's where XAI comes in. What is XAI? It's simply explainable AI. It means developing AIs that is human understandable, so that the decisions that it makes are understood and trusted. That's at the core of XAI. There are many types of XAI. We'll start from the simple ones where we're explaining the data. Instead of explaining the AI systems, we're explaining what the data it is trained on, so that in hopes we can understand why it made certain decisions. As you can imagine, when the data becomes very complex, it is not very easy to explain the data itself. Then we move on to explaining the AI models. AI models, it can be explained either wholly or partially using something like a proxy model. So what that means is AI model itself is complex, but we can sort of approximate its behavior using a simpler system and explain the simpler system, trying to explain the model itself. Again, when it comes to more black box model, where we do not know what is happening, what calculations are being done inside the AI model, it becomes very difficult. That's where post hoc explanations comes in. Post hoc explanations do not try to explain the whole model. It tries to explain the decisions, specific decisions made by the model. One way we can do that is giving examples, so example-based explanations. One example is, I guess we can just talk about counterfactuals as example-based explanations. So what counterfactuals is simply giving counterfactual examples, meaning contrary to the facts, the original case and the decision compared against similar case but with a contrary decision. So something like you go to the bank, ask for a loan, you get denied. A counterfactual example would say, what if you had asked for this only this much loan, you would have been approved, or if you had a monthly income of this much more, you would have been approved. So those are counterfactual examples and explanations through counterfactuals. So again, I kind of described this, but what is counterfactual? It is a post hoc explanation, meaning we're explaining the decision rather than the model itself. It is example-based, giving counterfactual specific examples and contrary to the facts. We can understand this with simple example. Let's look at, like I said, credit approval system, right? We will simplify this to 2 dimensions where we're only looking at the income of the user and then the credit amount requested. In this case, we see that the income was $52,000 and the credit requested was $7,500, and the prediction from the model was denied. When we look at the big picture, how the model looks, we can see something like this. The x-axis represents the credit request amount, the y-axis represents the income, and then the line we see here is the model itself. The line separates what is denied, what is approved. The gray zone represents denial, and the white zone represents approval. The single dot that you see is data point, represents the user. So the user can have any income, any credit amount. It represents to one point in the 2-dimensional space, which represents, which either falls in the approved zone or the denied zone, which is the outcome of the model. So in this case, we see that the user was denied. So how can we explain this decision using counterfactuals? So we can give one simple counterfactual example that is just increasing the income amount so that it moves from inside the denied zone into the approved zone. What that means is moving from $52,000 to $57,000. That's one counterfactual example. Another one can be just keeping the income same and decreasing the amount of credit requested. That means moving from $7,500 to requesting only $6,500. With the same income, with this model, it gets approved. Similarly, another counterfactual can be a combination of both, increasing the income slightly by $2,000, decreasing the credit amount slightly by $500. This becomes another counterfactual. So, as we can see, there are many different possible counterfactuals. All of them together give a picture. One thing to note is not all counterfactuals are the same. For example, in this case, if you look at this counterfactual where we're asking the user to have $5,000 more income, it's probably not possible for the user to just generate $5,000 more income on a short notice. So that goes to highlight properties of effective counterfactuals. What counterfactual examples are effective in conveying the meaning of the model, the decisions of the model better to the end users. And these are all, counterfactuals in general is dependent on the end user. It's not dependent only on the model, it's dependent on the specific user that's trying to use the model. One quality is proximity. What that means is the generated counterfactuals typically should be closer to the original data point, meaning if I change the values of income or requested amount very largely, it's probably not as meaningful to the end user because that's nowhere near what they wanted or what they were in the first place. Another one is validity, meaning that if the counterfactual data point falls within the desired class, it is valid. If it falls not outside the desired class, it is not valid. Saying like, if I was in the denied zone and the counterfactual that was recommended falls in the denied zone, it's not a valid counterfactual. Another one is sparsity. It's harder to see in the two-dimensional space, but if we imagine a n-dimensional space like with 10 features, 20 features, it's more easy to change a few features to reach a counterfactual than to change all 10 of them. Changing 10 different things by small amounts is probably harder to understand. Another one is plausibility, meaning that counterfactual should not be an impossible case. For example, it should not say that your income should be $200 million or something like that. It's not plausible. Another one is discriminative, means the counterfactual and the original point should be distinguishable by the user. If they appear to be the same, why is this approved and the other one not approved? Similarly, actionability, again, this is very dependent on the user. Some users might be able to generate more income. Some people might be able to request less credit amount. But then again, some people might not be flexible on that at all. They need that much credit. Finally, causality, meaning that there are some obvious causal relations in the data set which should not be violated. All right, so how typical counterfactual explanations work is they try to optimize some of these qualities. So some methods optimize for proximity, meaning they're trying to find the closest counterfactual point. Some optimize sparsity, meaning they're trying to change the fewest number of features to get to a valid counterfactual. Some try to optimize for validity. One example that was presented in one of the first papers on counterfactual was by Wachter. In the first portion of the loss function, it is trying to optimize validity, meaning the distance from the desired class versus the counterfactual class is trying to be minimized. And in the second element, it's trying to minimize the distance from the original class, meaning that it's trying to be valid while trying to be as close to the original as possible. So that's how typically counterfactual explanation methods work. Well, so notes on that. Again, it is focused on optimization and algorithms. It is less it involves the users very sparsely, meaning the users give the original data point and just get the counterfactual points. They're not involved in validating those. They're not involved in editing those. Another problem is the counterfactual explanations are very static. They give a few counterfactual examples, and that is it. The user has to try to understand the decision based on those. If they don't, that's tough luck. And finally, the biggest problem is they lack visual explanation. If you get just the counterfactual example, what it is, what the counterfactual is, trying to understand why it is so is difficult to understand if you don't get the visual explanation. It is easy, like we discussed earlier, in 2 dimensions, but it is important to note that when we're talking about large n dimensions, it is not very easy to visualize it. So that's where WiXAI comes in. What is WiXAI? It is a what-if exploration framework, giving the users a method to explore their what-if scenarios. It is interactive and iterative, meaning the users can interact with the framework, and not only once, they can keep changing small things, trying to see what differences it makes, trying to explore all the what-ifs questions in their heads. How this helps is not only they can understand the model better, understand the decisions better, they can also test their understanding by exploring, okay, if what I think is right, it should be this. And they can make those changes and see the changes in the final visualization. And if they are correct, they can bolster their understanding. WiXAI is also primarily visual explanation. To to get an overview of the framework, let's look at the typical machine learning AI system. What happens is after the modeling process, we generate a machine learning model, and the user is just giving their input and getting a prediction. WiXAI just plugs itself in between, gets the metadata, which currently is just the name of the features and the range, and it takes the user's input and sends it to the model and uses the prediction to get prediction as well as provide explanations, primarily visually. But it also allows the users to make changes, asking what-if questions, and then updates those visual explanations. Did you have a question?
So can we say that WiXAI is like an interface to the model?
Yes, it is a explanation interface to a model. Yeah.
Kind of like the GPT model, basically.
In what sense? How so?
In the sense of the what-if questions.
GPT is a generative transformer.
It's more general, but would you say this is more specific to a certain application?
So I think the GPT itself is a very, it's sort of a different thing than a typical machine learning AI model. GPTs don't typically predict. It's not a classification or regression model, right? It's trying to generate a large number of text based on the user input. But a typical system in AI machine learning, they're trying to classify or predict the value. So in that sense, I wouldn't say it's the same. What happens when you ask the GPT what-if questions is just it's getting a new input based on previous inputs, outputs, and the new inputs. It's predicting itself. It's not giving you a what-if, actual what-if scenario. Yeah. Okay, and okay, let's talk about the visualization within WiXAI. So the problem is we've seen that we can easily understand the two-dimensional visualization. The problem is when we have a large number of dimensions, it is not possible to visualize it in 2 dimensions. So the proposal is using projections of the model into n number of one-dimensional space. So n-dimensional model gets transformed into n number of one-dimensional space projections, and then together they form a 2D graph. I will explain how that looks later. What it does is it gives the view of the model from the perspective of the user, and it helps understand the user's position in relation to the model. So instead of just looking at the entire model itself, we're looking at the model from the perspective of the specific user. Let's look at a simple example, this time using 3D ellipsoid. We can see the equation for the model down here, and the single data point is -10, 10, 15. We can imagine this as one classifier model, where if it falls within the ellipsoid, it's class blue. If it falls outside, it's class white. Currently, it's outside, as we can see. So how this would look as a projection in a WiXAI is seen in this. You can see the black lines representing the shadows for the point, representing where the data point itself is. And each bar represents one feature axis, meaning the first one is x-axis, the second one is y-axis, the third one is z-axis. So how to interpret this? What it means is for feature x, when we keep all the rest of the features constant, no matter what we do, it always falls outside the zone, right? Same with y. If we keep x and z constant, no matter what we do to y, it always falls outside the blue zone. But for z, what happens is when we keep x and y constant, we can still go inside the zone into the ellipsoid. You can see the change from when we just change z value to try to move it to the inside of the zone. as you can see, it slowly moves inside the ellipsoid, and because they are related, the z-axis is related with x and y. What happens is it also changes the projection, how the model looks with respect to x and with respect to y. That's why the changes in projections are observed. When we look at just y-axis, we can see from here that if we increase the y-axis value slightly, we should be able to come outside the zone, right? And that's exactly what we observe in both in 3D and in the projections. We change the value from 10 to 11, it reaches the border. From 11 to 12, it comes outside the zone. Finally, just to test this out, we can see that the x-axis, the classification boundary is to the right. If we increase the value by a small amount, it should reach inside the classification boundary. And that is very much what we observe. Just the x value is changing. The y value, z values remain constant, but the projections itself change because how the model looks from the y-axis, z-axis when we change the x value changes over time. All right, so let's focus on the framework, how the framework actually works. We saw that the framework just plugs in between the model and the user. Let's look at the framework itself in detail. As you can see, there are many components that make the framework work. Key thing to note is the user is only interacting with two windows, interaction window and the visualization window. The user can give their input in the interaction window and make changes to query their what-if questions. And also they will get their predictions and explanations in the visual form from the visualization window. The other thing to note is that the machine learning modeling process is separate. It happens outside of the WiXAI framework. It is not related to classical machine learning process. We get the model and the metadata from it, and we're just plugging those in. Finally, there's a lot of calculation that goes into creating those explanations. First thing, we get the user's data, we create many counterfactuals and send them to the model to get predictions. Based on those counterfactuals and predictions, we're using the algorithms engine to generate explanations and projections. Those projections are then used to create graphs, which then give explanation to the users. And as you can see, it's an interactive and iterative process, meaning the users at any point can make changes and the entire process iterates. To give an example of how it looks in practice, in the file selector, we select what the model is. In the metadata selector, we select the metadata. And the user is then prompted to initialize their values. In this, this is an example with German credit data set. It has 20 features. The users can input what their current data is to get predictions and then get initial explanations. This is what the interaction windows look like. Here on the left side, you can see that there are some discrete features and some numerical features. The discrete features can be selected, while the numerical features can be changed via a slider or input window. And based on those inputs, the graph on the right side changes. Key difference here is, for example, attribute 1, 3, 4. Those have four distinct values instead of continuous value like numerical values. So, for example, attribute 1 has 4 possible values. That's why they're distinct 4 cases instead of having a continuous bar. The black line represents where the user currently is. Yeah. So let's just look at a simple example with WiXAI using a simple math model. In this case, we're looking at a problem with 4 dimensions, x1, 2, 3, 4. And the range for all of them is from 0 to 20, just for a simple explanation. the rule for the classification is if x3 is less than 10, it is class 1, or if x1 and plus x2 is greater than 20, it's also class 1. In all other cases, it is class 0. What does that mean? x3 less than 10 is an independent cause of class 1, right? The class 1 is independently caused by this rule. x1 and x2 are partial causes, meaning that they're dependent on each other to create the class C1 class, and x4 is a non-cause, meaning that no matter what happens to x4, it cannot change the class one way or the other. Let's just look at one simple case where all of the values x1, x2, x3, x4 are initialized at 10. The projections look like this, meaning that x1, if x1 increases slightly, we go to the other class, class 1. If x2 increases slightly, we go to the other class. x3, if we decrease slightly, we go to the other class. For x4, it doesn't matter, it stays in the same class, right? So how does that work? x1 plus x2 is not greater than 20, so it's not causing C1 yet. x3 is not less than 10, so it's not causing C1 yet. So if we just decrease the value of x3, it becomes less than 10, so it goes to C1, and thus the projections. Let's look at what happens when we change the value of x1 from 10 to all the way to 0, meaning that we're moving away from the classification boundary. We can Well, we can see that as we move away from the classification boundary, the x2's classification boundary also moves away from it. Even though the value for x2 is not changed, the projection itself, the boundary itself changes. It's because x1 and x2 are directly related, meaning that if one gets closer to the boundary, the other one gets closer to the boundary. If one moves away from the boundary, the other one does the same. We can sort of see this in the next one, where we can move the x2 value towards the classification boundary, which is to the right, meaning increasing the value. And what we observe is the classification boundary for x1 moves closer to the point. Thus, we can observe not only the relation of the test case data point towards the classification, we can also observe relations within the features. Let's look at third case, just x3. We reset the values to 10. If we increase the value for x3 from 10 to 19, what we observe is there are no changes in the other projections. Why is it so? Because x3 is an independent cause. It does not affect the projections. It does not affect the classification rules for any of the other features. So x3 is an independent cause, and we observe independence in the projections. Similarly, for x4, what happens is, from the rule, we understand that no matter what happens to x4, it's not going to affect the classification, right? And we observe the same thing in the projections. We change the value all the way to 19, doesn't matter. We bring it back all the way to 1, it doesn't matter. None of the other projections work. The class x4 by itself is also not able to change the classification. Finally, when we want to achieve a valid counterfactual, we can change x3 from 10 to 9, meaning the first rule, x3 less than 10, applies and it changes to class 1. We could also do the same by increasing x1 or x2 so that the sum is larger than 20. For this one, we can just see that x3, when we change from 10 to 9, it goes to the other class. Interesting thing is the projections for all of the others change, and more importantly, x1 and x2s become a non-factor, because what happens is when x3 is equal to 9, it itself is the cause of class 1. No matter what happens to x1 or x2, it's not able to change it back to class 0. Let's look at a more standard data set, German credit data set. We will focus, like I mentioned, there are 20 features, but we will only focus on 4. Attribute 2 represents durations in month, meaning how long I'm asking the credit for. Attribute 3 is the credit history of the customer. Attribute 5 is the credit amount requested. And attribute 8 is the installment rate in the percentage of disposable income. So smaller the percentage, better it looks. Similarly, output is class 1, meaning good credit, or class 2, meaning bad credit. This is a simple example for that. We can see that the values are such, and it can be seen in the projections. We will try to see how it looks when we change the values for attribute 2 in this particular case. When we increase the value for attribute 2, we observe changes in attribute 3, projections change, as well as attribute 5, meaning the projections, the classification boundary is getting closer to the sample, and as well as in case of attribute 8, the classification boundary gets closer, meaning that all of these attributes, all of these features are directly related, part of the partial causes of the classification. In the next one, this is the final point before it changes the class. So what happens is when we go to the other class, projections change, meaning we reached the other side of the boundary. We reset the value, and let's observe similar things on attribute 5. In this one, we have to decrease the requested credit amount to go from class 2 to class 1, meaning going from bad credit to good credit. What happens is if we slowly decrease the value for requested credit amount, the attributes 2, attributes 3, attribute 8 also show changes. Means it reinforces the fact that these are partial causes. Same with this. This is the final point before it crosses over. When we cross over, it reaches the other boundary, and we observe changes in the current class for all of the projections. Finally, let's look at just attribute 3. This is credit history. One important thing to note here is that attribute 3, the first value represents the user has no credit. The second and third means the user had credit but sent it back. And then the last two represent that they have outstanding loan. So one interesting thing we observe from this is that currently it's class 2, but if the users had outstanding debt that they were still paying, they would have been considered a good, good credit. And that's just something that's sort of counterintuitive, but something that can be observed using projections like this. So when we just change the values, we observe the changes in other predictions, and we also observe what I just described. All right, so just to conclude, let's look at why WiXAI, right? It is interactive, iterative, meaning the users can interact with the framework. They can also iterate and explore what-if scenarios, right? Users are at the center of explanations. The explanations are not focused on just the model itself. They're focused on what the current user is, what the current value for the user is. Explanations are also visual, and visually we're guiding the users to explore what-if scenarios. And finally, it helps the users to understand and test their understanding, meaning not only you're walking away with some rules that you understand, you can put those rules to test and see if they hold true or not. We published this paper, like Dr. Kantarjit mentioned, in June of 2024 in Journal of Computer and Communications. And then we're currently working on expansions. Currently, possible directions are using distribution of the data set, not only just the name and the range, but also the distribution to more inform what are more valid counterfactuals, what are more plausible counterfactuals. Another one is generating guiding counterfactuals, meaning instead of just letting the users generate whatever counterfactuals they can, we can generate some counterfactual points that act as guides so that they know what directions they can head into. Another one is looking at regression problems instead of just classification, and also comparing optimization of minimum distance versus prototype counterfactuals. Prototype counterfactuals are counterfactuals that represent entire class instead of just being close to the user's data. And finally, not only using records data, but expanding it to text data. Citations for the presentation. Thank you.
Thank you.
If you have any questions.
Thanks a lot. Do we have some questions or comments? Anything about? Okay. Maybe one question from presentation would be, okay, you are changing one feature, and at once the others are changing. And it looks like, based on presentation at the moment, they are changing, but essentially I don't know how you are computing these changes. It looks like all the time you are talking that Wix is independent from machine learning model. But essentially all these changes only is possible based on a machine. So you have to go, and it is very time-consuming computation then to record these changes.
Yeah, so as we, in the framework, so what happens every time we make changes, every time the user interacts with the window, the changes are sent to the data engine, and it generates many counterfactuals based on those. So every update, we have a number of counterfactuals that are sent to the model, and we get predictions for those, and then the visualizations change. It is thus interacting with the machine learning model, even though it's not directly part of the WiXAI framework.
In some instances, does it affect things like, suppose credit score? That's one of those things where like there's a lot of parameters and decisions are made based on certain things, multiple credit scores. What does it mean for like, how common is it for the accuracy of the model to be hidden for it to be somewhat accurate? Because they don't disclose how credit scores are always computed, correct? Some aspects of those parameters are hidden because once people become aware of them or how it reacts, they'll start manipulating behavior. Is that completely disjoint from this, or?
So that's the exact nature we're trying to solve, right? With credit score, okay, it's a government, or I guess like a trusted entity, so you're trusting the decisions. But there is no transparency. There is no inherent trust for the users. Which is why we have a lot of sentiment of distrust with the credit system. The issue we're trying to solve is exactly that. Instead of having like we have this expert system, don't worry about it, it makes the decision. We're trying to show the users, like, you can ask questions, you can try to understand it, and it should ensure even more trust, rather than just saying, like, there is an expert system somewhere that you don't know about, that we don't understand, we should just trust it. I feel like that is not a recipe for good trust. Like, even though, like, I understand you don't want to disclose some secrets, this is not where I guess it's applicable. This should be more applicable where the users are trying to understand and trying to trust the system, not just taking their word for it.
Good. Any additional comments, questions? What is the next step? It is develop the framework.
The next step.
It is working. What?
The next step.
Is it PhD already finished?
No.
Or?
Definitely not. So the next step is, like I mentioned, to use distributions of the data set. So what that means is, right now we're just looking at what are the names of the features, what is the range of the features. But what distribution helps with is maybe the value, for example, having credit request amount of 3 years, 4 years is probably, like very infrequent, very unlikely. So suggesting the users to go and do that is probably not a good counterfactual. So using distributions, we can inform them, hey, yeah, we can, model says you can go to the other class using this large number, but it is very rare to see it in real life. So it's not a good idea, probably not a good idea to go down that route. Probably you should look at other features to change. So something like that, integrating that is one of the first next steps.
I'm a bit curious, can I ask another?
Mhm.
When I'm looking at this panel here, you said that this framework is kind of disjoint from the actual model part of it, correct? How does this get implemented? Did you create this? Is this a Java?
I implemented this using, because like I did not have time to learn a new one, I just used Python. So this is using PySide 6, which is a Python wrapper on the Qt framework, which is very common in like cross-platform development. But that one is C++. This one is just a Python wrapper outside of it. And it is open source.
These things exist, is that correct?
Yeah. This is an existing thing that runs, and like I wrote that using the PySide 6 open source library. I think, yeah.
Yeah, so the visualizations, are they only limited to one dimension?
What do you mean
Like
one?
the graph that we see here.
Mm-hmm.
So is it the only type of representation that the model?
Yeah. So it's representing, for each feature, it's representing a projection from the view of the data point. So it is trying to visualize where you are in the feature space, and then where the model classification boundary, where the model lies in that feature space in relation to you. But yeah, it is one-dimensional right now. It seemed more readable to do so, because if we start giving it 2 dimensions, you can imagine how many graphs it takes, right? So like choose 20 choose 2 is what? But it's a large number. It's a large number. It's it's in factorial. So it's like going to 2 dimensions, 3 dimensions, it becomes like even more complicated to like not just compute, but to like understand from the user's perspective.
Maybe we can just use, instead of having all the attributes, we can just choose a few attributes and then have a.
That is possible. Yeah, that is possible.
And what does it mean? If you have 100 attributes, how you are presenting 100 of them? So we're ordering the attributes in terms of sensitivity. So how sensitive they are to go to the other class. So ranking based on those. And then we can see, like down here, we can have pages of features. So each page contributes to X number of features to be shown. So you don't have to have a 100 by 100 graph. Okay. It looks like a nice environment for playing. You're playing a little bit up, a little bit down. What you are getting from this playing?
The end goal is for the users to understand the framework, understand the decisions made by the model, to gain trust, so that they know that the model is consistent.
Okay, that is a phrase, gain trust. Everybody gains trust. But how I can gain trust? I'm trying here and trying here and trying here. What kind of additional information I'm collecting in this gaming a little bit with these counterfactuals?
Playing with, like you said, quote unquote, playing with this and generating like each change generates counterfactuals. Using those and observing the changes in the graph, I showed you can see relation between the features. You can see relation with features and the output. So that is the goal, like for the users to be able to understand that.
When people start playing with this, sometimes models, if you remember in your first few slides, you had that kind of graph that was kind of going up, and it wasn't monotonically increasing. So it almost gave the impression at some point a person could make so much that goes down. So is it possible that when people are gaining trust that they actually observe the model have jumps in maybe what we might think as continuity? And all of a sudden they
Inconsistencies.
Like, oh, this makes no sense, but this is what the model's doing.
Yeah.
It may seem counterintuitive.
That,
so that causes distrust.
That is like important in the sense that even the machine learning model creators themselves can look at it and say, oh, the model's not behaving quite right in this scenario. We can look for biases using this. For example, like in this credit system, let's say there was one feature that was just the gender or something. And if we keep everything else consistent, just change the gender and observe like the chances of getting credit goes down, that's an inherent bias in the system that is like demonstrated using the system.
In the machine learning model.
Yeah, in the machine learning model. So this is sort of independent of the model. The flaw is in the model itself. The framework is sort of highlighting that, I guess.
And don't forget, when the model is making mistakes, so the system is not recognizing these mistakes. It is predicting as the model is predicting. We are assuming, and that is the basic idea, model is doing as it's doing. Let's understand how the model is behaving and how the model is working. That means it is not that the system is trying to improve or increase the quality of the model. No, it is interpretability. Whatever is model, I'm trying to stand behind the model. That means it is wrong, it is wrong. It is good, it is good.
Yeah.
So that is the basic idea. Interpretability is that user is becoming much closer to the model, nothing else. It is not the question, okay, let's go find the better model. Yeah, but that is the other problem. Okay.
Also, on that note, I guess this goes into philosophy and not really related to this. Oftentimes what we observe is that when the system itself is imperfect, what people try to do is hide the imperfections rather than try to expose it. And what that leads to is just more fog around the system, more distrust. Using like open source, using exploration of the model and inviting criticism kind of allows you to fix those issues rather than try to run away from it. I think that's just that's not related to this, just philosophy.
Okay. Do we have any?
Yeah. So usually we have to train the model first, right?
Mm-hmm.
So in this case, are we training the machine learning model itself, or do we have something in the framework that we are training based on this data?
So the machine learning model, the machine learning process is independent of the framework. We're assuming that the model exists, and we're just trying to interpret it to the user. So it is not part of the framework. The model just plugs into it.
Okay. I see there is no any additional comments. I would like to thank one more time our guests.
Thank you.